Woo! All right. Ladies and gentlemen, welcome back to section 4 for day 1. Today we're talking about a brand new topic called optimization. So, this is a really fancy sounding word, but really all it means is we're going to find a max or a min. And lucky for us, we've already gone through this. We know the steps for finding a max or a min. What's going to make optimization a little bit different today is when we do an optimization question, we are trying to find a max or a min within a context. So typically this is going to be in the form of like a word problem. This is not just, hey, here's a function, tell me what the max is or the min is, local, absolute, whatever, right? Now we have to think about the context of the question and which makes sense to find a max or a min. So let's take a look at an example. So, first example here says find two non-negative numbers. So non-negative, right, could mean a few things, but definitely not negative, whose sum is 20. So two non-negative numbers whose sum is 20 and whose product is as large as possible. Okay, so this is everything we're given here. Find two non-negative numbers whose sum is 20 and whose product is as large as possible. Now, this is a kind of a simpler example. I think a lot of you look at this question, you could probably just flat out come up with the two numbers in your head, which is totally fine, right? But we're still going to talk through the steps of how do we do this sort of question, this sort of optimization question. What should the steps be so that we can do this again in a more difficult scenario? So here's what I like to do on an optimization question. I like to establish three things, okay? The first thing is what I call the primary equation. This is what we are trying to optimize, right? And remember, optimizing means finding a max or a min. So what are we trying to find the max or the min of here, right? Well, if we look back at the scenario, it says whose product is as large as possible, right? That means we are trying to maximize the product, okay? So I'm going to call the product P. I don't know what the maximum product is, so I have to call it a variable, right? And the product is going to be the product of two numbers. Do I know the numbers? No. So I'm going to call one of the numbers X and the other number Y. So this is going to be my primary equation. P equals XY. So again, the reason we have a P here is not because this is the primary equation, but because the thing we're trying to maximize is the product of two numbers. So the product function, right? Or excuse me, this is not a function, right? Because there's two input variables here, X and Y. We'll get to that in a little bit. But the product equation is what I want to be as large as possible. Next up, we have secondaries. So I write secondary equations here, but as you'll see here, these can also be inequalities, okay? So secondaries are going to be some limits or restrictions in the scenario that are going to prevent us from making the product, in this case, as large as possible. Because couldn't I let X be 1,000,000 and let Y be 100,000,000 and then get a gigantic product? Well, I can't because I have a limit here, a restriction that says that the sum of the two numbers has to be 20. So my two numbers are X and Y, so I'm going to turn that into an equation. X plus Y equals 20. And that is going to be my first secondary equation. Now, another limit or restriction I have here is that my two numbers, X and Y, have to be non-negative. So what does that include? That includes positive numbers, right? But it also includes 0. So X can be greater than or equal to 0, and Y can be greater than or equal to 0. Okay, so here are my three secondaries, right? These are some limits or restrictions on X and Y that are going to prevent us from making the primary as large as possible in this case. Okay, and the last thing I like to do is establish something called the SIE, the single independent equation. So Single independent refers to a variable, right? So remember, there's independent variables and dependent variables. So what this is going to be is my primary equation, right? So let's go back here. So in the primary equation, P is the dependent variable. It depends on my two independents, X and Y. So what I'm going to do here is I'm going to take my two independent variables, X and Y, and I'm going to swap one of them out, okay? And here's what I'm going to do. And now here it actually doesn't matter which one you pick, but I'm going to go ahead and pick Y. Okay, and so my goal is to replace this y with something. And so what we do is we go to our secondaries, right? And I look right here and I go, hey, x plus y equals 20. I can solve that equation for y, and I get y equals 20 minus x. And what I can do now is I can take this value for y, plug it into my primary equation, and now I'm going to get a primary function. P is now going to be a function of just x because it is going to be x times the quantity 20 minus x. And now, to make our work a little bit easier, I'm actually going to go ahead and distribute here. So I get 20x minus x squared. And this is my single independent equation. This is the equation that I'm trying to find the max or the min of. And again, in this case, since P represents the product, right, I want the product to be as large as possible. So I'm trying to find the maximum of P of x here. Okay. So once we get our single independent equation, now the next steps are going to be great because these are all the steps that we already know how to do. We're just going to find the maximum for P of x. So what's our first step in finding a maximum? We need to establish the domain. So domain for this one, right? Well, now we can look back at the secondaries, right? X has to be greater than or equal to 0. So my domain is going to be bracket 0, comma. And now here's a question. What should the upper bound for x be? What's the biggest possible value for x? And what we can do here is actually do a combination of my secondaries. So I know that y has to be greater than or equal to 0, right? And I also know that y is equal to 20 minus x. So that means that 20 minus x has to be greater than or equal to 0. And now this is an inequality that I can go ahead and solve. And that would tell me that x has to be less than or equal to 20. And that becomes the upper bound for my domain. Okay, so it's really important with these questions, especially with the domain, right, to assess whether we can have brackets or parentheses. Because in this sort of a question, we're not just trying to find a maximum, we're trying to find the absolute maximum, right? We want the product to be as large as possible, okay? So having endpoints here matters because, right, these are possible places that the maximum could occur, okay? So that's step one, that's the domain. Now, step two, critical numbers. Let's take my single independent equation, P of x. We're going to take its derivative, so P prime of x is going to be 20 minus 2x. And now we're going to set P prime equal to 0. We're going to set P prime equal to does not exist. And so P prime equal to 0, 20 minus 2x, set that equal to 0. You guys know how to solve that. We're going to get x equals 10, and that is going to be my first critical number. And 20 minus 2x is linear, right? And so it's going to always exist. One of the two most common mistakes I see people make in optimization questions is they forget to check where the derivative does not exist. And the second most common mistake I see people make with these questions is they go straight from step 2. They find a critical number and they want to go straight to step 4, right? And determining what the answer to the question is. But be careful here. We still need to confirm if my critical number is indeed a max or a min. And so the nice thing here is that you have options, right? You can choose to do the first derivative test, which we know and love. But for me personally, I'm a second derivative test kind of guy, right? Especially with a function like this, where the second derivative is really, really easy to find, right? P double prime of x is negative 2. So what is the second derivative at my critical number? Well, it is going to be always negative 2, right? And so what does this tell us? This tells us that we are concave down, right? Because the second derivative is negative. If we are concave down at a critical number, second derivative test tells me that I must have a local max at x equals 10. Okay, so one of the most common mistakes people make in optimization questions is that they skip this step. Step 3, you have to check and see whether your critical number is indeed a max or a min. You can choose to use first derivative tests if you want to test those intervals 0 to 10, 10 to 20. You are more than welcome to. I like second derivative tests, especially when the function is something as simple as 20 minus 2x. Okay, so we do second derivative tests, and now we can finally answer the question here, right? Step 4, I have endpoints, so I need to check 3 possibilities here, okay? So first possibility, right? What if the largest product occurs when x is 0, the left endpoint? Second possibility, what if the largest product occurs when x is 20, right? So take 0, take 20, plug them back into p of x, and you're going to see actually that you get the same answer for both of these, right? 20 times 0 minus 0 squared is 0. 20 times 20 is 400, minus 20 squared, also 400. We get the same product, which is 0. And the last thing I need to do is just make sure, what is the product when x is 10? 20 times 10, 200, minus 10 squared, which is 100, we get 100. So the biggest product does indeed occur at my local max, which tells me it's my absolute max, right? And now I can finally answer the question. And this is another place where people can sometimes make a silly mistake. What did the question actually ask us to find? If we scroll back up, it says find 2 non-negative numbers. It didn't ask me to find the maximum product, right? Now I had to find the maximum product to determine that I indeed get my absolute maximum from here and not one of the endpoints. But the question is actually asking us to find the 2 numbers, which in my work are labeled x and y. So I know one of them is x equals 10. Now I need to solve for y. And conveniently, I've already solved for y. Y is 20 minus x. So I'm going to come down here into the next question real quick, right? Y equals 20 minus 10. And so we get that y is also 10. And so what are my 2 numbers? They are 10 and 10. That is my final answer. So another common mistake with optimization questions is actually going back and answering the question, right? You have to look at what the question asked to find. It didn't say find just one of the numbers that gives the maximum product, right? It didn't say to just find what I've labeled as x. It said to find both. So my answer is 10 and 10. Okay, so main thing I want you folks to take away from this today is not steps 1, 2, 3, and 4 here. You all know how to do that, right? The main takeaway is going to be what we did in the beginning, okay? Taking a scenario, right, and being able to figure out how can I use this and come up with a function of just one variable so that I can now use my process of either the first derivative test or the second derivative test to find maxes and mins. This is going to be the challenge. Okay? Okay, let's do another one. So, next example, very similar to this first one. You have 80 feet of fencing to create a rectangular pen surrounding your garden. What dimensions will give your garden the largest possible area? So again, we want the garden to have the largest possible area. So again, we are trying to maximize something. This part in parentheses here is not going to be given to you when you take a future quiz and test. You're going to have to figure that part out yourself. Okay, so I wanted to do a geometric example here, and we're going to do a couple of geometric examples because what I want you to get in the habit of doing is, first of all, drawing a picture, always useful, right? We have a rectangular pen here. I have two sides labeled X and Y, but also just making sure you fully understand before you do too much, what do your labels mean? What does X represent in your work? What does Y represent in your work? Okay, because that's gonna make a huge difference. Okay. Okay, my goal is to maximize the area. So I'm gonna call the area the letter A, right? And also in the future, I'm gonna be using these shorthand initials here for primary equations, secondary equations, and single independent equations. So we're never gonna write out the full things like we did above, okay, the full labels. All right, so my primary here, I'm trying to get the largest possible area, so area is going to be the output here. And how do I calculate area? Well, some of you would say length times width, and that would be perfectly fine, but those are not the labels in my work, right? So I'm going to go with X and Y. Okay. Okay, so that's my primary equation, right? Maximize the area of this rectangle. Now, what is secondary? What is limiting us from making the area of our beautiful, pristine garden as large as possible, right? Well, this is where we look at the first thing that's listed here, which is we have 80 feet of fencing, right? That's a limitation, right? If I have 80 feet to make the fence to go around this rectangle, right, that is going to limit the maximum area we can have, okay? So what do we call this, right? What is this measurement? 80 feet of fencing to create the rectangular pen, right? We should be calling that the perimeter, okay? But here's the thing, I actually don't want to use the letter P because I know that the exact perimeter is going to be 80 feet. And now, how do we calculate perimeter? We have to add up all the sides, and so we get 2x plus 2y, okay? And now, it doesn't mention this like it did in the last question, but, right, if I'm making a physical object, right, if I'm making this actual rectangular pen, right, can the dimensions of my garden be 0? No. Can they be negative? No. So X has to be greater than 0 and Y has to be greater than 0. Okay, so this is something we have to understand just by looking at the scenario, right? We can't build a garden with a negative length or a negative width. Okay, if you figure out how to do that, please let me know. Okay. Okay, now I need a single independent equation. Okay, so let's come back to my primaries, and now this is arbitrary. It doesn't matter which one you choose. Sometimes there's a nicer one to pick, but it really doesn't matter. I'm a get rid of Y kind of guy, right? So I'm gonna get rid of Y by going to my secondary and solving for Y here, right? And if I solve that equation for Y, I get Y equals 40 minus X. And now I'm going to take this equation and I'm going to plug it back into my primary. And so I'm going to get that, whoops, wrong tool. I'm going to get that the area as a function of just X is going to be X times 40 minus X. And now I'm going to take this and I'm also going to distribute just like last time, just because it'll make my derivative work a little bit easier so I can use some power rules. But this is my single independent equation right here. This is what I'm actually going to find the max or the min of. Okay? So now, step one, let's find a domain. So we know x has to be greater than 0. Again, x is a side length in this rectangle. It cannot equal 0. So I have to go parentheses 0. Okay, and now what's the maximum? So just like last time, right, I can do a little bit of a combination here, right? I know y is greater than 0, right? I also know that y is equal to 40 minus x. So I'm going to set up a little inequality here, right? And this is going to give me the upper bound for x, okay? So 40 minus x is greater than 0, right? Which means that x has to be less than 40, and that is going to give me the upper bound for x. Okay, and if you're still not sure on why exactly it's 40, I want you to think about this, right? What if x was 41? Right? If x was 41, well, then the opposite side would also be 41, and that would be a combined 82 feet of fencing, which means that the other two sides, the two y's, would have to be a combined -2 feet of fencing, right? That doesn't make sense, okay? So we can use some logic there as well to help figure out things like that, okay? Okay, but that's step one, okay? Step two, my single independent equation, I need to find critical numbers, so let's take a derivative, right? And so a prime of x is going to be 40 minus 2x. We're going to set a prime equal to 0. We're going to set a prime equal to does not exist. So set that equal to 0. We're going to get x equals 20. That's a critical number. And can a linear equation ever not exist? Nope. So we get none from that. Okay. And now step 3, one of the most common mistakes people make is they assume that this critical number is what we want, right? But we have to prove it. So your choice, first derivative test or second derivative test. Again, I'm a second derivative test kind of guy, right? A double prime of x is going to be -2. So my second derivative at 20 is going to always be -2, right? Which means we are looking at concave down at a critical number, which means that we have a local max at 20. I don't need this second arrow here. Okay, so the work on this question is almost the exact same as the last one, right? Step 4 is going to be a slight departure though, right? Because I have no endpoints to check here, right? No endpoints to check, okay? So now we can actually just go and look at some facts, right? We know there's a local max at x equals 20, right? And so none of these endpoints are included. So this local max has to be my absolute max, okay? So we don't have to worry about that. So step 4, we can just answer the questions, right? What dimensions will give your garden the largest possible area? So we can find the largest possible area, right? We can take 20 and plug it back into our area function. I'm going to do that. Even though the question doesn't ask for it, I am curious, what is the largest possible area? So 40 times 20 minus 20 squared is going to be 800 minus 400, which is 400 feet squared. Okay, so that is the actual largest possible area, but that's not what the question is asking for. The question wants to know what dimensions will give your garden the largest possible area. That means x and y. So we already know what x is, and just like last time, we've already solved for y, right? And so if we calculate that, right, 40 minus 20, and I'll do that to the side here, y equals 40 minus x, so 40 minus 20 is 20. So that's going to be the y value. And now the last thing I'm going to do is answer the question with units. This is another thing in optimization questions we have to look out for. Okay, so what are the correct units going to be here, right? So everything is given to us in feet. So x is 20 and y is 20. So the answer is 20 feet by 20 feet. I use an x in the middle for by. You can also just write the word by there if you want as well. Okay, but these dimensions with units will give us the largest area possible. Okay, so again, very similar work as the last question. I just want you to get a feel for how we are setting these up. Okay, so let's take a look at one more of these sorts of questions today, and that'll be the next one at the top of the next page. So what do we got here? It says a rectangle is to be inscribed under one arch of the sine curve from 0 to pi. So before we look at anything else with the question, I want to talk about what this means. So I already have that arch of the sine curve drawn here. So y equals sine of x, right? That's my curve. From 0 to pi, it's going to look like this, okay? Typically with these sorts of questions, you'll get a picture. It's not guaranteed, okay? But here I decided to give you the picture, all right? So let's talk about what this means, okay? So when it says inscribed, right, underneath this arch of the sine curve, what that means is there's going to be a rectangle that's going to look something like this. And I'm going to do my best to draw this rectangle. Okay, and now I'm going to make the width of this rectangle come all the way down to the x-axis. Now, some of you might be asking, well, why are you going all the way down to the x-axis, right? Well, that's because we want to make the rectangle as big as possible, okay, right? If I stopped right here, right, and my rectangle was like that, well, I could make it bigger, right? So that's exactly what I'm going to do. I'm going to drop this down to the x-axis. So the x-axis is always our stopping point. Okay, because if we didn't stop at the x-axis, we would just go on down forever and ever. So we got to stop somewhere. So might as well be the x-axis. So I'll stop there, right? I'll put another one here. Okay, and now here's my rectangle. So this is what it looks like when it says it's going to be inscribed underneath the curve. So it's always beneath the curve, but above the x-axis. Okay. Okay. So what are we looking for now? What is the largest area that the rectangle can have, and what dimensions give that area? Okay, so I'm trying to optimize the area, right? I want the area to be as large as possible. Now, for my primary equation on this one, I'm going to go A equals length times width. The reason I'm going with L and W here is because X and Y in this picture already have a specific meaning, right? X and Y refer to the ordered pairs that make up this sine of x curve, okay? So I'm going to go with length and width when talking about the dimensions of this rectangle. So that is going to be my length, right? And this is going to be my width. Okay, also I like to use a cursive L whenever I write length, just because if I go like a lowercase l, then it just looks like a 1, and uppercase, that's too fancy. We'll stick with cursive, okay? But that is my primary equation, right? I'm trying to figure out what is the largest area that this rectangle can have, okay? So what are my secondaries, okay? So my secondaries here are going to be a little bit tricky. And now what I ideally want to do here is not just get area to be a single independent equation, but I actually kind of want to get rid of L and W because I want to deal with X and Y, right? Which again have a different meaning in this, right? So let's talk about what X and Y mean. So I'm going to zoom in on this curve, okay? What do X and Y represent here? X and Y represent something like this point right here, right? That is X and Y, right? That means that this little sliver here is X, and then that is going to be Y, right? X comma Y means X units over from the origin, and then Y units up or down, Okay, and so if we think about x and y, we see something very important here, right? And that is that the width of this rectangle is indeed going to just be y, right? The width of the rectangle is y. Okay, but more importantly now, how do we figure out y? Well, very luckily for us, we have an equation for y. Y is the sine of x. Okay, so let's slow down and let's talk about this again. Okay, x comma y in a question like this is going to represent something very important. It is going to represent this kind of like ordered pair here, this point of intersection between the rectangle and whatever function you have that the rectangle is inside of. Okay, and so x units over from the origin and then y units up is going to give you the width for this rectangle, okay? And now we know that y is sine of x, and so follow along with me here now, right? That means that my first secondary equation is that the width is equal to sine of x. Okay? So the width is sine of x here, all right? And now, since I'm making a rectangle, I also know that the width has to be greater than 0. Okay, but we'll come back to that. Okay, now let's talk about the length. So if I look along the x-axis here, right, this arch of the sine curve is going from 0 to pi. But the length is made up of the part that's kind of like in the middle, right? On the left, I have this part x that's cut out from it. But I also have this part on the right here that's also going to be cut out from it. And actually, this length is also going to be x units long. And that's because the sine curve is going to be symmetrical here right through its middle, which is right in the middle of 0 to pi, right? And so we have a little gap for x on the left there on the x-axis, right? So we have this little gap here along the x-axis, and then we also have that little gap on the other side, which is going to be symmetric. And so that tells me then that the length for this rectangle is going to be pi minus an x on each side. So the length is going to be pi, so again, 0 to pi units long. Take out an x on each side, right? This x comes out, right? This x comes out, pi minus 2x's, and that's how you're left with just the length of the rectangle in the middle, right? And now I also know that the length has to be greater than 0. Okay? And the last thing I know is that since this part of the sine curve is kind of like in quadrant 1, right? I know that x is going to be greater than 0. Okay. So let's substitute my equations for L and W into my primary, and that'll give me my single independent equation. So area as a function of just x is going to be the length, which is pi minus 2x, times the width, which is sine of x. Okay, so this is the calculation for the area of my rectangle. Okay, and now we have our primary. So let's get started with finding our max, right? So let's start with the domain. So we know x has to be greater than 0, right? Because we're in quadrant 1, right? X is positive. Okay, so we are going to be parentheses 0, comma. Now, what's my upper bound going to be here for x? Well, let's think about it. X is going to be the part along each side of the x-axis that's going to be cut out, okay, in order to get the length of the rectangle. So can x be pi units long? Well, no, then there wouldn't be a length, right? So it has to be less than pi for sure. Okay, but if we combine these two up here, these two secondaries, right, just like we've done on some of the previous questions, right, if L is pi minus 2x, but L is also going to be greater than 0. That tells us some very important things here, right? So that means then we can set up an inequality, right? Pi minus 2x has to be greater than 0. And now we can solve this inequality and get that x has to be less than pi over 2, which makes sense, right? Because we're cutting off x on each side of the rectangle, right? Pi over 2 from the left, pi over 2 from the right, that would add up to pi. And so it has to be less than pi over 2, right? And it has to be parentheses because if we go equal to pi over 2, well, then the length would be 0. Okay? So the domain is 0 to pi over 2 here. All right? And now I want to show you how to do this sort of question on a graphing calculator. Okay? So let's say I asked you to find this, what is the largest area that we can have? Okay? So what you would do, right, and this is what we're going to do now, steps 2, 3, and 4, right? If this was a graphing calc question, you would do all of these steps on the graphing calculator. And so we're not going to actually write out any work for that, right? But we still need to show the work of setting up, hey, here's my primary, here's my secondary, here's my single independent, and most importantly, you have to establish a domain. When you see the graph of this function, you will see why domain is so important here, okay? But we're going to do the rest of the steps on the graphing calc, okay? So here's what we're going to do, and I'm just going to show this to you on Desmos for now, okay? Pi minus 2x times sine of x is my single independent equation, right? Remember, this is the area function, right? This is the area with an input of x. Keep that in mind when we actually find what the maximum is. So I'm going to go to Desmos, and I already have it graphed here. Wonderful. So a of x is equal to pi minus 2x times sine of x. And one thing you'll notice right away looking at this graph is there's a few maximums here, right? And so if I'm going to zoom out here just to show you how many maximums there are. And, there's a few, right? There's a few maximums here we could be talking about, right? Is it, can I even touch any of those? Nope, there's too many, okay? So, this is why domain is very, 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 very important, okay? Because we need to make sure that we're talking about a specific maximum, not every single possible one, right? We set our domain to be 0 to pi over 2, right? And pi over 2 is, like 1.57-ish. So if I zoom in to about there, right, now it becomes super obvious, right, that is the maximum I am looking for, okay? 0.7105, comma 1.1222, okay? So let's write this down, okay? The result of steps 2, 3, and 4 on the graphing calc, I get 0.711, around to 3 decimal places, and 1.122, okay? Now, that's what I get, but another important thing we have to do, and this is what I was talking about just before we went to Desmos, is you have to look at this and know what each part of this represents, right? Because what do these things mean? What does the 0.711 refer to, right? Well, that is the x-coordinate, right? Because that is the input for the function that I graphed, which is a of x, right? And a of x is the output, okay? And so what do each of these things mean? This is super important here, right? When you are setting up your work, you have to have a full grasp of what every variable represents, okay? Right? X is going to be, right, this distance right here from 0 to the start of my rectangle, right? A is going to be the maximum area. And hey, what were we trying to find? What is the largest area? So this maximum, 1.122, is the maximum output for our function here. That does represent the maximum area of my rectangle. And no units here because, it didn't give us any, okay? But 1.122 is the maximum area, right? We graphed the area function. We found the maximum on our domain, right? And the y-coordinate of that, right, is not a y-coordinate here. It is the output of this function, a of x, and a represents the area. So that's the maximum area. So that's one part of what this question asks for. The other thing this question asks for are dimensions, right? And now, again, you have to know what everything represents. X is not a dimension in this rectangle, right? L and W are, and very conveniently, we have L and W as functions of x. So that's exactly what we're going to calculate now. L is pi minus 2 times 0.711. So you can go ahead and calculate that, right? And we will get 1.722 approximately. And the width is sine of x. So what is the sine of 0.711? Make sure, by the way, just a reminder, right? All calculus is done in radians here. We should be in radians from the very start of this, right? Sine of 0.711 is going to be 0.652. And so the dimensions that give me the largest possible area are length by width, right? 1.722 by 0.652. Okay, so again, main things I want you to take away from these examples we've looked at today, right, is how do you analyze a scenario? How should you set it up? Okay, primary, what are your secondaries? What are your restrictions, right? And lastly, what is the single independent? What am I actually going to try to find a max or a min of here, right? Steps 1, 2, 3, and 4, this last example we did on the graphing calc, but for the most part, these steps are going to stay the same, okay? So we will pick up tomorrow's lesson with the next example here, and then one more off 4.4 day 2. I will see you then.